Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, height of a binary tree after subtree removal queries. The problem is very interesting. If you haven't given it a try, I would encourage you to pause and give it a try yourself. We will be discuss. There are a lot of different ways to solve this problem, and we will be discussing in this video Euler tour, which is one possible way to solve the problem. I am intentionally describing Euler tour because you can apply the same technique in lot of different questions. It basically transform your tree into an array. And now solving, like we know a lot of different algorithms to solve things in an array, like segment tree, penvic tree, and other range queries, data structures are there. So there are a lot of things that we can do on an array, prefix, suffix, sum as well. So that's where I would explain that Euler tour in this approach, in this video, and I am very sure that if you watch the video to the end, you will be able to apply Euler tour in other questions in future as well. And I will make sure that I will start from the very basics, so everyone who doesn't know Euler tour can understand. But the assumption is you already know DFS, how to do DFS in a tree. That's all. Okay. So with that, let's start. And there is one more follow-up question to this problem as well, which is a little harder than this, which I would encourage you to solve, and we can discuss the solution in the comment section below. Okay. So the what is the question? The question is, you are given a tree rooted at some node. You have to answer m number of queries. What is the query? Query states that I will like remove entire subtree rooted at some node x, and then find me the height of the remaining subtree. That's it. So let's say this is the tree, and query comes as 4. So what does 4 mean? 4 means remove the entire subtree rooted at 4. So I have to remove this entire subtree. And if I remove this entire subtree, I will be left with this tree. Now the what we need to return, what is the height of this remaining tree. That's it. So hope the problem statement is clear. Now about follow up. So here we are given that the queries are independent. That is, after every query, the tree will return to its original state. So let's say the first query was 4, so we have to find the height of this tree. Now let's say second query was 3. So this 3 would not be removed from this subtree, from the remaining tree. 3 would be removed from the original tree. So after every query, the tree will be reset to the original tree. So after watching this video, I would like you to think about the case where this constraint was not there and try to answer it. Okay. uh, Watch the video, try this yourself, and then we can discuss the solution in the comment section below. You would appreciate this. So let's start. First, you can't actually do brute force. So what is the brute force approach? Let's say you remove 4 from here, and if you got some tree, remaining tree, something. Now brute force would be to just uh, do a DFS and find out the height of the tree. But that would mean that we will be doing a DFS for every query, for each of these m queries. So what like there are m queries, and we will be doing DFS for each of those m queries. Doing DFS in a single tree, in worst case, requires order and time. So what will be the time complexity? Time complexity would be order n cross m. So here n is 10 to the power 5 and m is 10 to the power 4. So the complexity would shoot up and will not pass for this particular problem. So we have to do something better. So let's see. Let's first try to simulate the problem as always, and then we will try to build the solution upon it. So first, let's say you have to remove the entire subtree rooted at 2. Okay. Now what you have to find the height of the tree, right? So let's say you already found the height of the entire tree. So height of this the tree rooted at here is 0. Height of this tree, like height of this tree is 0. Height of this tree is 0, right? Similarly, height of this tree is 0. Now height of this tree is 1. Basically this particular piece is 1. Height of this tree is again 1. This tree height is 1. Height of this tree is 2. This entire piece, right? And height of this 3 would be 3. Again 1 and 0. So this is the height of the tree. Now let's say you have to remove 2. Now if you remove 2, will this number change? The answer is yes, because this 3 would not be 3 anymore, it will become 2, right? So this number would change. Now, if this is a small tree. Let's say there is a big tree which has several other nodes. So and we are removing something from here. So everything here would be changing, right? Then height of this entire piece would change. And in case, like in worst case, the tree can be just a linear linked list. And to update the height of all of this, we would require order and time, right? So this would also not help. So first of all, if we need to perform some query, like we have to perform a lot of queries, right? So we can't afford updating all the nodes every time. So we have to come up with something such that we don't need to update the value of each node. Or basically we need to come up with something such that this whatever data structure we will choose, the value in that data structure would not change, or even if it's change, it will change for few of the values. So we have seen that in this case the change is happening for a lot of values, and we can't actually perform this change with any kind of range query data structure, right? So that's where we have to come up with something such that this value doesn't change, or even if it change, it will change for few of the nodes, not n number of nodes in worst case, right? So let's think about it. We have found out the what we have removed this entire subtree, right? So removing this entire subtree actually means that we we have lost all these nodes. So if there is a way where we can, where this node represent what will be the height if this node was there, if there is something like this, then we can surely say that removal of this nodes or removal of this subtree would not take any effect on any of the values. To reiterate, currently these values are changing because of removal. Now we have to come up with something such that these values, whatever values that those are, they may not be height, but whatever values those are, they would not change. So what we have said is, current why this is changing because this value depends on what is there below, right? So if you remove something from below, this value would change. But we are not removing something from above, right? Let's say there is something above this, and this value, whatever value this is, depends on whatever was there above this. So if it depends on the above node, this value would not change, because this value doesn't depend on the tree we are removing, right? So just to make things clear, let's say we, instead of storing the height, we store the depth. So depth of this tree is 0, depth of this tree, depth of this node. Basically, previously we are saying that this node means this entire subtree, right? Now we are saying that this node means everything above this, right? So now this two wheels means everything above me, right? Similarly, this 3 would mean everything above me, right? So now the depth of this 3 would be 1. Now depth of this 4, 5, and 6 would be 2. And depth of 7, 8, 9 would be 3, right? Now think about it. Now if you remove something, let's say you remove this entire subtree, okay? This subtree is removed. So what is the value? What is your answer? The answer will be the maximum across the remaining nodes. That's it, right? Again, previously we are not able to find this because the values are changing, but now values will not change. Whatever you have removed, that is removed, okay? Whatever is remaining, the values of those would not change because they are depending on their ancestors. And now we can say whatever is the remaining node, we can just take the maximum and we get the answer. Okay. Now if you think about it, you might be getting an intuition of a range query here, right? But we can't apply range query on a tree. We know how to apply range query on a array. We have a lot of algorithms for this: prefix max, prefix suffix sum, or prefix maximum, suffix maximum, segment tree, family tree, and all these things. But we can't apply range data structure on this tree easily. Okay. So now the problem reduces to finding, or basically, or rather converting this tree into a linear array, and then we will do a range query for getting what is the maximum across a range. Got it? So if you are not clear till this point, I would encourage you to watch the previous 5 minutes and you will get what we are trying to do. So the problem now we are trying to solve is just convert this tree into a array and such that whatever is remaining can be covered in a single range L to R. And now we will apply some range square data structure to find the maximum across this range L to R. Okay, so hope this makes sense. Now let's try to think how we can convert this array to a range to an array. Like sorry, convert this tree to an array. Okay, so first first thing. So now let's say what you are doing. Let's say you converted this to array. So what property this array would have, like what exactly this property this array would satisfy. We are removing a subtree, right? So this array should satisfy that if I am removing a subtree, this subtree should be some subarray of this array, right? Because otherwise it will be hard to find out what is the maximum. Let's say uh, 2 is here in the array, 4 is here in the array, 5 is somewhere here, and say 7, 8, 9 was somewhere before this. Okay, 7, 8, 9, and this is your array. Now can you do any kind of range query data structure here? The answer is no, because you can see you, even though you have converted this to array, this removal of subtree is not a subarray. And because it is not a subarray, you can't apply any range query data structure here. You again have to iterate over the entire array, pick them up individually, and then do something with them, right? So you can't apply range query data structure. So to apply range query data structure, you would want a subtree to be a subarray of your converted array, right? So that's what the property we need to satisfy. Now let's see how we can satisfy this. So like it is very simple. It is just a DFS. So what what a DFS, like let's say you are doing DFS. You start with this node, okay? You go to the left, and now you come here. Now think about it. When will you visit this node? You will visit this node after you have explored the entire subtree, right? Then only you will visit this node, correct? So if that is the case, if you just lay down these numbers in the order you are doing DFS, automatically a subtree here would be a subarray in your array. Okay, let's take an example. So let's say you are doing DFS, okay, and we will just lay down our DFS values here. So we are doing DFS. We start with 1, so let's put 1 here. Now we go to 2, let's put 2 here. Okay. Now we go to 4, let's put 4 here. Now we go to 7, let's put 7. Then we, before going to 5, we will go to 8, right? That's what we do in DFS. So let's put 8 here. Then we will go to 5, right? Because everything of 4 is exhausted, so we'll go to parent and do the DFS from there. So we will visit 5, and then we will visit 9, right? And then everything here is exhausted, so we'll then visit 3. So 3 is visited, and then we'll visit 6. So we visit 6. So now notice what we are claiming is this is the required array. That's it. This is the Euler tour of your Euler tour of your tree. Now notice we have to make sure that every subtree here is a subarray here. Now how that is true? We have discussed it briefly. So basically what we are saying is DFS has this property that it will visit the entire subtree first and then only go to the parent, right? To visit the other nodes. So because of this property of DFS, this tree, like any subtree here, should be a subarray here. Let's verify this. Let's take 4. So 4, like what is the subtree of 4? 4, 7, 8, right? So see this part, 4, 7, 8. This is a subarray in this particular array. Now let's take 2. So in 2, what is the subtree? 2, 4, 5, 7, 8, 9, right? So let's see this part, 2, 4, 7, 8, 5, 9. So this is a subarray. This entire subtree is a subarray of of our in our converted array, right? So hope you are convinced that this is correct. If not, just try to think about it in this way. Let's do a DFS. Let me remove this. So now let's start DFS. So you will start DFS from here, right? So you will visit this. Now you will visit this. Now you will visit this. Then this, and then you will visit this, right? And then you will visit this. Then this, and then you will visit this and this, and finally you will be here, right? So now notice this. Before going to this, you are traversing this entire subtree, right? Similarly, this property is true for every node. Before going to any of its siblings, you are visiting the entire subtree first. So that's where this property is true. Okay. So now we have converted our tree into an array, and we also make sure that whatever value was there uh, is a subarray here. Like whatever subtree is here is a subarray here. Now let's say query comes. Query comes that remove 2. Now remove 2, it means that remove this subarray, right? Now removing this subarray, what we have to find? We have to find. If you remember previously, we have calculated the depth of each of these nodes. Let's do it once again. So we calculated the depth of each of this node, right? And why we calculate depth? Because height would require values to be changed and depth doesn't require, right? So now what we have said is, if we remove something, if we remove some subtree, we will remove some subarray from here, and we have to just find out what is the maximum of the remaining numbers here. So here the value of 1 is 0, value of 3 is 1, and value of 6 is 2. So the maximum across this is 2, and that's what we have to return, right? So how we can find out the maximum? You can apply segment tree here, but a very simple approach could be find the prefix sum, find the suffix max, sorry, find the prefix max and find the suffix max. And for whenever you have to remove some range L to R, just take the prefix max of previous element of L and next element of R, right? So this will give you the maximum across this prefix max, and suffix max will give you the maximum across this, and you can just do the maximum of both to get the final value. Okay, so that is it. That is the solution. So now let's just iterate over this once more to just get a feel of it. We How we will build this array? We are clear. We just do a DFS. Now, while doing DFS, we can calculate the depth as well. Okay, and further we don't have to find the maximum across these numbers. We have to find their values. So after calculating this array, we will calculate another array which will contain the depth of each of these. So depth of 1 was 0, depth of 2 is 1, depth of 4 is 2, depth of 7 is 3, right? Depth of 8 is 3, depth of 5 2, and then 3 1 and 2. Okay, now you will calculate the prefix max over this array, and then suffix max over this array. And now you know that removal of some subtree here is a subarray here, removal of some subarray here. So you will get LNR. How we will get LNR? We'll look at it, but you will get LNR. And once you get LNR, you can just do maximum across the prefix max before this index and after this index. Okay. So hope this solution makes sense. Now only thing that remains is how to calculate this L and R. So this is very simple. Notice that we are doing DFS. So we'll start from here. Okay, let's remove this numbers, or maybe not. So we'll start from here, right? Let's change the color. We'll start from here. We will go there, there, and then this, right? We are going this way, right? So while coming from here, we can keep maintaining an index. Let's say index was 0. Let's say our index is 0. So initially 1 will be at 0, right? Now we will go to 2. So whenever we will start a subtree, we will maintain its starting index as well. So for 1, we will maintain so for each of these index, we need to maintain a pair where this is starting, where this is ending, right? And why we need to maintain this pair? Because for every query, we need to understand which subarray to be removed, right? So that's where this pair we need to maintain. So this maintaining this pair is again very similar to the DFS. What you will do, you will just maintain an index. Now let's say you visit one first. So you will do, okay, one is starting from zero. Okay. Now you visit 2. So you will say, okay, I will increment the index because one node is visited. So 2 is starting from 1. Now you will visit 4. So again, before visiting 4, you will increment the index. Now you visit 4. So 2 is starting from 4. Sorry, 4 is starting from 2, right? Like this 4. Forget about this. This is a value array, right? So 4 is starting from 2. Now you increment it again, and now visit 7. So 7 is starting from 3. Okay. Now you increment it again and make it 4. But now you will see that 7 doesn't have a left or right subtree, right? So 7 is exhausted. So before incrementing, you will mark it as ending index as well, because you have visited, like this start will denote when you started this node. Now this end will return when everything in its subtree is visited. So because 7 has no subtree or no nodes beneath it, it is ended here. Now you will visit 8. So again, you first remove, increment, and then uh, this is the starting of 8. Now again, there is no subtree of 8, neither left neither right. So 8 is ended. So because 8 is ended, you will mark end as well. Okay. So increment it to 5. And now before incrementing it, you will, because 8 is ended, you will reach 4. Now once you reach 4, you will see that, okay, 4 is already exhausted, like left and right of 4 is already exhausted. So before incrementing, you will mark the end of 4 as the current index. So end of 4 is 4. 4 was the current index, right? Now again, you visit 5. You have incremented our I and visit 5. So 5 would be starting at 5, right? Now you visited 5 already. Now you visit the subtree of 5, which is 9. So you visited new node, so increment it. So 9 would be starting at 6, right? So you now increment it, but before incrementing, you check whether you have visited all the subarray, all the subtree. So you have visited all the subtree. So this is the ending. So 9 would be ending at 6 only, right? And after you have done this, you will go to 5. Now 5 is already exhausted. So 5 is also ending at 6. Now after you have done this, you will go to parent. You will see 2. Okay, 2 is already exhausted. So now because 2 is already exhausted, this is the ending of 2 as well, right? So hope you get the intuition how to build this starting and ending array, right? So just to reiterate what we have done, we have first find out the Euler tour of this tree. Euler tour is just a fancy name. We are just doing a DFS and just maintaining, just keeping an array of the nodes in which order they are visiting in the DFS. Now, once we have done this, we have to maintain starting and ending of each node as well, because what we are saying is each subtree here is a subarray here. So we need a starting and ending as well. So because we need a starting and ending as well, we are maintaining a counter, and whenever that subtree was completely visited, we will just mark the end, and while entering, we'll mark the start. Okay. Now, once you have this start and end, you can simply answer the queries by seeing the prefix and maximum and suffix, like prefix max and suffix max, and you will get the answer. Okay. So hope this makes sense. Let's look at the pseudo code that will make things much more clear. So what we have done, we have calculated the ST and ED for each node. This is basically by doing a DFS and maintaining this counter. Okay. Now once we have ST and ED for each node, we calculated the depth of each node and arrange it in the order of Euler tour. Basically, we know that this is the order of the Euler tour. So we will just calculate this array based based on this node. So basically, first 0 denotes that what is the value, what is the depth of 1. Similarly, 2 denotes what is the depth of 4. Okay, so we calculated this depth. Now we calculate the prefix max of this array and suffix max of this array. Once we have this for each query, we know L and R would be ST of Q and ED of Q, right? And then we will just result equals to just maximum of prefix of L minus 1 and suffix of R plus 1. So this is our L to R. We have to remove this entire thing. Now removing this entire thing means whatever suffix, whatever prefix was there, just find out the maximum. Whatever suffix was there, so just find out the maximum, and maximum of these two in turn would be our answer. Okay, so hope this makes sense. Let's look at the code. Uh, so code is very simple. What we have done, we have counted the number of nodes. This count node is just a simple DFS function, which is just counting the nodes. Okay, so we counted the nodes. Now we have made our ST, ED, and depth array. Now we are doing a Euler tour, and if you remember, we have to maintain the indexes as well to find out the start and depth. Okay, so let's say you do this Euler array, yeah, Euler tour, and you calculate the depth. Now, once you have the depth, you will just find the prefix max across the depth and suffix max across the depth. And finally, for each queries, you have L and R, and just you will your answer would be maximum of prefix of L minus 1 and suffix of L, R plus 1. So the only thing that remains is this Euler tour. Let's look at that. So Euler tour is again, as we discussed, we have to find ST and ED for each node. So we are not actually making this array. Okay, instead of making this array, we are directly finding out the ST and ED. So how we are doing this with this counter? Now ST of current value is the current index. Index is the index at which is free right now. So index, ST of this is index. Now if there is a something in the left, I will increment the index. Okay, and after I increment the index, I will again call Euler tour on the on that particular subtree. Similarly, if there is something on the right, I will increment the index and call Euler tour again. Now after these both are visited, so we have visited both left and right, and notice that this index is a reference. So this whatever you are doing here, it will be reflected across your life cycle of this function. So the, once you reach here, all these things are executed. Index will be pointing to the last node in the current subtree, right? So that's what you want. You want the end index of the current subtree. So you will just put ed of this as index. Okay. So hope this solution makes sense. If you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. I hope you learned something new. So you can actually apply this algorithm, uh, or either Euler tour, which is nothing but just a DFS order. You can apply this algorithm whenever you feel that you have to do some kind of range query data structure, whenever you need a range query data structure on to be performed on a tree. Now, whenever there is a query that you have to remove the subtree, right? You can actually use Euler tour. That is applicable there. So whenever you see that you have to remove the subtree and you have to find this, find something based on the remaining tree, you can use Euler tour, and this is only possible. Like, I'm not saying that this will be always possible. This is only possible when the values of the remaining node will not change. Okay, even if it change, it will change for a like minimal number of nodes, like not n number of nodes for, let's say, one or two nodes. So hope you enjoy the solution and learn something new. If you like the video, give it a thumbs up and do subscribe to the channel if you haven't already, and I will see you in the next one. Thank you.